All right, so we're looking at substitution. So we're first going to look a little bit about composition of functions, and then we'll talk about this thing called U-substitution. So when we're integrating things and it's hard because it's more complicated than just like a straight power rule or backwards of any of the rules that we've done already, then takes a little bit more doing, and we can tackle that. One of the ways we can tackle that is through U-substitution. So first, let's talk about composition of functions. There's an analogy of composition of functions where we're looking at functions, and I'm laughing because it feels silly, but it also is very helpful. So if we're looking at a function like f of x equals 4x minus 2 over x squared plus 3 quantity squared, there's an inside function and there's an outside function. The inside function we're going to call the peanut, and the outside function, these are peanut M&Ms. Sorry if I didn't mention that. These are peanut M&Ms, so we have peanuts on the inside and then M&M chocolatey goodness on the outside. So for this, what's the inside function? Like f of x, if we're gonna say that f of x is a composition of functions, where we have h of x is x squared and g of x is 4x minus 2 over x squared plus 3, then which of these is the inside function? It's g of x. So g of x is the peanut. So we have g of x on the inside. And then all of that quantity is being squared, so we have h of g of x is our function f of x. So when we're taking our derivative, f prime of x is going to give us h prime of g of x times g prime of x. So now, if we were looking perhaps at our antiderivative of f prime of x, then we need that, right? H prime of g of x times g prime of x dx. Okay, so going from here, we can get back to our original f of x. So then the question is, effectively, if we're starting here at our h prime of g of x times g prime of x, if we can identify what the inside function is, if we can identify the peanut, then we can figure out what our original function was a little bit more effectively than just trying to like look at it, think to ourselves, what do we do? And then just like it falls out of your brain. Doesn't always work. Sometimes it works and that's awesome, but generally doesn't tend to happen. So identify what is the inside function, and then we can do something called U-substitution. So let's look at a formal write-up of that. So if we're looking at antidifferentiation of a composite function, so composition of functions, let g be a function whose range is an interval I, so we're looking at an interval, and f be a function that is continuous on I. Continuity implies integrability. If g is differentiable on its domain, differentiability implies continuity, so that's good. G is differentiable and continuous. And cap f is an antiderivative of little f on our interval I, then integral of f of g of x times g prime of x dx equals cap f, so our antiderivative of f, of g of x plus c. So what we're doing here is we're saying u is the peanut. U is the peanut in our peanut M&Ms. So du is g prime dx, and this du equals g prime of x dx. That is just looking at if u is g of x, then du dx is g prime of x, yes? And then if we just take our differential and we multiply it over, du equals g prime of x dx, similar to our linearization stuff that we were doing. Okay, so then we can write this in just the same thing, except instead of having g prime dx at the tail end, we just have du, because du is g prime dx. And that's really lovely. Okay. Typically we use u for our substitutions, so we call this u substitution, but you don't have to use u. That is just a convention. That is what I'm probably going to use, but, you know, if you want to do a different variable, you do u. Okay. So, what is the inside function? What's the peanut for a? For a, what's the peanut? What's the inside function? So for a, the inside function is this x squared plus 1. So that means that u is x squared plus 1. So du is 2x dx. So that means that this 2x dx, that is du. So I'm going to rewrite for part A. What do I have? I have x squared plus 1, which is u, to the 4th power, times du. And what is that? U to the 5th over 5 plus c, constant of integration. And u to the 5th over 5, well, that's going to equal x squared plus 1 to the 5th over 5 plus c. And there we go. That is antiderivative of a. So that's my indefinite integral, evaluated. All right. So for part B, what is the inside function? What's the peanut? I think it's x to the 3rd plus 1. So let's work with that. So we have, for part B, we have u equals x to the 3rd plus 1. That's our inside function. So that means that du is 3x squared dx, and that's lovely because that's right there. Fantastic. So we have root u not x, du. And what is that? That's u to the 1/2 power. So then we can power rule that. U to the 3/2 power over 3/2, which is the same as multiplying by 2/3, plus c. And let's sub in what we had for u, put it back in terms of x. So we have 2 times x cubed plus 1 to the 3/2 power all over 3 plus c, because we're responsible and we don't forget our plus c. Okay. What about for letter C? What is our peanut? What's the inside function? I think the inside function here is tangent x plus 3. And why, Ms. Contreras? Why is that our inside function? Well, if we're thinking, we need the derivative of the inside function to be somewhere. Secant's derivative is not just tangent, right? Secant's derivative is secant tangent. Secant x tangent x. So that's frustrating because that's not right there. So what about tangent x plus 3? Is that derivative, is tangent x plus 3's derivative represented here as secant squared? Yes, because the derivative of tangent is secant squared. So I guess we'll just go sideways on this. Okay, so we have, for C, our inside function, our peanut, is tangent x plus 3. So du is secant squared x dx. And this means that our integral, our indefinite integral, is with secant x dx, secant squared x dx, that's just du, and u is just all we have right there. So we evaluate that, and that's u to the 2 over 2 plus c. And then we substitute in our original u, which was tangent x plus 3. And slide over a little bit. Tangent x plus 3 quantity squared over 2 plus c. And boom. There you go. I was a barbarian over here, and I did not box my answers. I am sorry. Alright, there we go. So that's A, B, and C. The goal really is to the challenge is to identify what's the inside function. Or if we want to think about peanut M&Ms, what's the peanut? So let's do some examples. So look, these are two separate problems. So how are we going to how are we going to evaluate our indefinite integral there? Well, what's u? U, here I think it's x squared plus 1. So du is 2x dx. Now, does 2x dx show up here? Kind of, but not really. Because we have x and we have dx, but we don't have this 2. So how do we get rid of the 2? Good old division. So we have 1/2 du equals x dx. So in our substitution, we're going to have 1/2 du, and then we have our u squared. And when we evaluate this, what are we going to get? We get 1/2 u to the 3/3, and that's multiplied plus c. And so that's going to be, what, 1/6 u cubed plus c. And what's u? I forgot, it was all the way up there. X squared plus 1. So we have 1/6 x squared plus 1 to the 3rd power plus c. There we go. Alright. How about for this one? What's the inside function? We have sine squared of 3x times cosine of 3x. So I think u here is going to be sine of 3x, which means that du is cosine of 3x, but here we have an inside function there. We got to chain rule that, so we got to multiply by 3 and then dx right there. But once again, we have this issue where our du isn't appearing cleanly. We have cosine of 3x dx, but we don't have this 3. So we need to divide. So we have 1/3 du equals cosine 3x dx. So that means that this is equal to integral of sine squared of 3x, which is u squared, and then cosine 3x dx, which is 1/3 du, so I'm going to multiply by 1/3 and du there. And the 1/3 can come out of the integral symbol because, or out of the integrand, because we have scalar multiplication. Scalar multiplication works very nicely. So what's our antiderivative? U squared, u to the 3rd over 3, and we're multiplying by 1/3 plus c. And so we have 1/9, and then u is sine of 3x, and we're cubing that, plus c. Boom. There we go. And if we're slightly concerned, because sometimes we are, we can check our work. And how do we check our work? Do you remember? We can just take the derivative. So 1/9 sine cubed of 3x plus c dx of this. And what do we get? 3/9 sine squared 3x times cosine 3x times 3 plus 0. That's not a 0. That's a 0. Okay. And then what do we get there? Well, 3, 3, and 9, those cancel, so we're left with sine squared 3x, cosine 3x, and I think that's it. Is that what we wanted? Is that what's in our integrand there? Oh yes. Good job, everyone. Okay. Perhaps it gets a little trickier if we're doing definite integrals. Indeed, it does get a little bit trickier. But this is there's a couple different ways of doing this. I don't really have a preference of which you do, but I'll show you both and see which one you like better. It also depends on the situation of what you feel like, what's more efficient. So, here we have a theorem. If the function u equals g of x, so that's the peanut, has a continuous derivative on the closed interval from a to b, and f is continuous on the range of g, so f is continuous on where it's being evaluated, which is the outputs of this continuous derivative g of x function. Then, our definite integral from a to b of f of g of x times g prime of x dx equals our function evaluated, our g evaluated at a, to our definite integral from g evaluated at a to g evaluated at b of f of u du. So what does that mean? So we need to find, first we need our inside function. What's our peanut? For this example, u equals x squared plus 1. And so du is going to be 2x dx, so 1/2 du is x dx, and that's good because that's what we have. So here's where the options come about. You can either do exactly what the theorem says, where you're looking at your function g evaluated at 0 and g evaluated at 1 and change your bounds. So g of 0 is 0 squared plus 1 is 1. G of 1 is 1 squared plus 1 is 2. So we go from 1 to 2 of u cubed 1/2 from here du. So we can evaluate that and go on our merry way. So we have what, 1/2 u cubed over u evaluated from 1 to 2. And what's that? That's 1/6 times u, sorry, not u, that's a 2. 2 cubed minus 1 cubed. So that's 1/6 times 8 minus 1 is 7. 7/6. Okay, so that's one option. Other option is to leave your bounds so that you don't have to deal with changing the bounds and evaluating this stuff. And you just need to make sure that you translate the whole antiderivative or your definite integral back into terms of whatever your bounds are in. So here, our bounds were in terms of u, our integrand was in terms of u. What if we chose to do the other way, which we're going to put in a different color? So we have our integral from x equals 0 to x equals 1 of, and then if we take this part, our translated integrand, then we have 1/2 u cubed du, and so that means that we have, when we evaluate that, we have 1/2 u cubed over 3, but we're evaluating from x equals 0 to x equals 1. So from here, we need to translate back into terms of x. So we have 1/6, and then u is x squared plus 1, and we're cubing that, and we're evaluating that at 0 and 1. And look, I dropped the x equals because now we have everything in terms of x. So now we have 1/6 times 1 squared plus 1 quantity cubed minus 0 squared plus, not 0, 1 cubed, and that is 1/6 times 2 cubed minus 1 is 7. 7/6. So these are both options. It doesn't really matter to me which one you do, but just if you're choosing to keep your bounds in the original, in terms of the original variable, then make sure that you note that, otherwise you're going to forget and you're going to plug it in like this and it's going to be sad. And if you're choosing to change your bounds to match what your integrand is in terms of, that's also totally fine. Just be careful about plugging in correctly. Okay. So try this one and we'll see how you do. So what's the inside function? What's a peanut? It's just so funny. Okay, so let's see. What should we do? I think we should do 2x minus 1. Alright, so let's do 2x minus 1. So u equals 2x minus 1. du is 2 dx. Whoa. So, what do we do now? Well, we do have this expression, or we have this equation, so we also know that u plus 1 equals 2x. And so, u plus 1 over 2 equals x. These are all things that we are having in our pocket to deal with our substitution. We should probably change our bounds, though. So, g of 1 is going to be 1. G of 5 is going to be 9. So we have a equals integral from 1 to 9 of, let's see, we have x in our numerator that we're going to substitute with u plus 1 over 2. And then in our denominator, we have root u. And then we have dx, so that's 1/2 du. My goodness. Alright, and now, then that was the calculus part pretty much. Now we just got to do some algebra, a little bit of calculus, and then we will be okay. So, let's see. What goes, well, we can factor out a 1/2 from here, so pull that out into the front. So 1/2 times 1/2 is 1/4. Integral u plus 1 over root u du. And this is from 1 to 9. Okay. This is kind of annoying, so maybe we should break that up. So maybe we should break that up so that we get 1/4 integral from 1 to 9 of u plus 1 over root u equals u over root u plus 1 over root u. Yes, because when we're adding fractions, we can have, like, combine them when they have a common denominator, and we can also break them apart. So u over root u, that's equal to u to the 1/2 power. 1 over root u is u to the negative 1/2 power. So u to the 1/2 plus u to the negative 1/2 du. Okay. And now that's a power rule. So let's power rule that. We get this equals 1/4. U to the 1/2. When we power rule that, it is u to the 3/2 times 2/3, which is the same as dividing by 3 over 2, plus u to the 1/2 divided by 1/2, which is the same as times 2. And we're evaluating that at 1 and 9, and then we're using fundamental theorem of calculus so that we can evaluate that nicely. We got 1/4 times 9 to the 3/2 power is, so we got 2/3 times 9 to the 3/2 is 3 cubed is 27, plus 2 times root 9 is 3, minus parentheses. Okay. 1 times 2/3 is 2/3, plus 1 times 2 is 2, and there we go. And now we're just doing a little bit more arithmetic, and we get this equals, well, 1/4. That goes to 9, and there goes away. So then we have 18 plus 6 is 24, minus 2/3 plus 2 is 2 plus 6 is 8, so 8/3. Let's see, 24 minus 8/3. Yeah, 24. Maybe we can distribute this 4 and do a little bit less mental math. So we have 4 times 24, 1/4 times 24 is 6, minus 1/4 times 8/3 is 2/3. Okay, so then 6 is, how many thirds is 6? 6 is 18/3, so 18/3 minus 2/3 is 16/3. Okay. Whew. And there we go. Yeah. That was a lot. But what were we trying to do? Oh, we were evaluating. We were evaluating this lovely integral up here, this definite integral. This definite integral from 1 to 5 of x over root 2x minus 1 with respect to x, and we got 16/3. Cool. Good job. Oh, is that it? Oh, I think that's it. Wow. Nice. 16/3.